We are 40 people now in this moment, so welcome everybody to this summer school, and you can start, Francesc.
All right, thank you. So my name is Francesc Moreno-Noguer. I am a researcher at the Institute of Robotica, and I'm going to talk about some of the work that we've been doing in our group in the last 2-3 years on modeling humans and their contextual interactions. So Xavi gave an excellent talk about the basics on deep learning. So here we will see some of the applications that we have done. And later on, Alberto Marola will explain some of the details that you can that we have used to do these works. So basically what we have been doing is the following. We want to capture different aspects of the human body. For instance, from single images, we want to be able to compute the 3D pose of the person, understanding the pose as a 3D skeleton of these people. Then we also have been working on, from a single image as well, to reconstruct deformable objects, right? Like clothes, pieces of paper, etc. And last year, we presented a paper where we did simultaneous reconstruction of the body shape plus the clothes the people were wearing. Sorry, I think there is someone with a mic on. I think it's Alberto Marola. Albert, can you please turn off the mic? Thanks. So in these 3 works, what we do is a regression from different geometric properties of the human, but we have also been working on a generative model to create new images. So in this work, we created an algorithm that given an input image, just one input image of a person, we were able to generate new images of that person as seen from different viewpoints. And also we worked on given one single image of a face, we were able to change the expression of this face. Well, in all these works, the estimation of the human properties is done by just taking the information of the human itself. But usually, human will live in an environment, and many of our properties depend on this environment. For instance, our pose can be highly defined, but the object that we have surrounding us, or our expressions also are dependent on the context. So in a very 2 recent works, we have started to introduce the context within our formulations, and we have done 2 works on here. Sorry, just let me go here again. Sorry. Okay, so we've been doing a work on motion prediction using the context, all right? And also in this very recent work, what we have done is grasp affordance. So this means given an input image of different objects, so we are able to estimate how a human would grasp these objects, all right? So in order to solve all these problems, we could use like brute force solutions. So we could understand deep networks as black boxes, and we could take our favorite deep network. Then we could set up the hyperperimeters and train it with as much data as we have. In this example, I see a case where the input data are images of people and the output are just a skeleton. We train with all this data and the parameters, and we cross fingers that everything will work. And if not, so we repeat the process again and again, changing the parameters, maybe changing the training and test splits, etc. But what we try to do, a common denominator in our work, is that what we try to do is we try to exploit geometrically aware components or constraints to improve the performance of these deep neural networks. So what do I mean by this? In particular, what we try to do is to find data representations with higher levels of expressivity that help the network. And also we try to design modules or architectures that inherently reason about the underlying geometry and appearance of the problem. All right. So what do I mean by this? Let's see one example here on body pose estimation. All right. So the problem here is the following. We are given an input image. So we assume that we have the 2D joints of this person that can be computed in a straightforward manner using open pose, alpha pose. There are many algorithms for this. So we are given this input image and the 2D joints, and we want to compute the position of the joints in 3D. All right. So the most straightforward solution for doing this is just to do a regression from the 2D joints to the 3D joints. But instead of using this representation of joints or the coordinates of the joints, we found it much more convenient use a representation based on Euclidean distance matrices. So here we had in the left side of the network, in the input data, we had 2D Euclidean distance matrices, where this matrix is an n times n matrix, where n is the number of joints, and every entry here is a pairwise distance in the image domain, all right, in pixels. And on the right, we have 3D Euclidean distance matrices, where every entry is the Euclidean distance in 3D between two joints. So we found that training on this kind of rectangular domain, which are these EDMs, these Euclidean distance matrices, was more convenient for exploiting, for instance, fully convolutional networks. All right, and we could build these fully convolutional networks, very small ones. So this is a very small network, just 600,000 per meter, 0.6 mega per meters. That's nothing compared to the networks that there are out there with hundreds of millions of per meters. And this could be trained really, really quick. And another good property of using these Euclidean distance matrices is that they capture very well the correlations between the joints. And I show this in this specific example where we have the input image, the 2D joints, and in this example, we have removed the joints, the 2D observations of the joints corresponding to the right arm. So the elbow and the wrist, which are these two columns and rows, are just removed from the input of the network. And besides this, we are able to estimate the 3D position of the joints. And you can see here at the bottom that the reconstruction of all the skeleton, and in particular of the joints corresponding to the right arm, which is not seen, seems very coherent. All right. So some more examples of this kind of representation, or more in the wild examples. Here, these are examples of people doing some crazy postures in the lead sport dataset. So you can see that this method also works here. All right. And that's what we obtained with this kind of representation using Euclidean distance matrices. So another aspect that, if I will be talking on different topics. So at the end of every topic, you can ask questions. So is there any questions so far? So I don't know. Maybe you can turn on your mic and question for completely. All right. So another work I wanted to we work at is in the following. So most of the approaches that were trying to solve human pose estimation, they estimated the pose of a person in a coordinate frame which was centered on the person. We didn't know how far was this person from the camera. All right. So we also worked then in absolute 3D body pose estimation. So for this, what we did, we created this absolute pose layer, which is a very simple layer, which basically given a network that from the input image estimates the body centric coordinates, this absolute pose layer estimated the absolute position of the person. And for doing this, we didn't use any kind of parameters. This was a parameter-free and fully differentiable layer, which exactly implemented the underlying geometric equations to compute the absolute pose. I will not go into detail on this, but it's just the idea that we can encode these geometric equations within a network, all right? And here I show you some examples. So on the top, you can see that we have the detections in 2D and the 3D detections of the people. So, and we don't have the ground truth, but by observation, you can see that the position of the people on the ground plane seems coherent. And also here in the bottom, you can see that the tensors, so the distance between them, it's also very consistent. So even when they cross, so here the units are in millimeters, so they are separated like 1.5 meters, so it seems very, very consistent. All right, so let's move to the next paper. Is there any question now for this part? You can open the mics if you want. If not, let's move.
Francesc,
yes.
I think you have a question by Abhishek. Will I move completely towards neural networks?
Well, this is a very generic question, but of course, well, I of course not. So neural networks will remain here, but they will be another like another tool that will. There are many tools in AI which cannot be substituted by neural networks. So it will come here. So it arrived. It will stay. It will become a very important part of AI. But of course, everything will not be deep network. So, and as you will see probably tomorrow and after tomorrow, you will see other solutions that, especially in robotics, that they don't use deep learning, and they also work very well. But of course, if you can exploit deep learning, so this will be very also important. So another question from Juan Delgado. Could you explain a bit how you estimate these 3 distances from 2D? All right, yes. So basically, what we have here, we train a network that we have the 2D Euclidean distance matrices, which are distances in the image plane, and we do the regression of the 3D Euclidean distance matrices. So basically, it's the network itself that learns this regression, all right? And probably what's missing here is that from these Euclidean distance matrices, you can compute the 3D joints using another algorithm, which is I didn't explain here, but is called the multidimensional scaling, which basically boils down to computing some singular value decomposition on top of this matrix to compute the 3D joints. But the transformation from 2D to 3D is done by the network. It's learned by the network using the training data and learning all these parameters within the network. All right. I guess I hope this answers your question, Juan. All right. So let's move to the next paper I want to talk about. All right, is this one on 3D cloth reconstruction. So here the problem is the following. We have a single image of a deformable object, a cloth, a piece of paper, etc. And what we want to do is to reconstruct the 3D shape of this deformable surface. All right. And before the deep learning era, we already had experience in solving this kind of problem in what I call these traditional approaches, optimization approaches that didn't use deep learning. And what we did in these traditional approaches was first to represent the surface as a mesh. Then we registered the mesh in 2D, and then we lift the vertices of this mesh to 3D using different constraints like isometry, smoothness, projection consistency, etc. Then we tried to emulate these 3 steps using a deep network. So that's the deep network that we used. On the left, you have the input image. On the right, the 3D shape that we obtained. And this network is made by 3 main branches that try to replicate what we were doing in these traditional approaches. The first branch is the 2D detection branch. That's basically a regressor that takes the input image and estimates the 2D position of each one of the vertices in the image plane, all right? So we estimate heat maps for each one of the vertices of the mesh. Then we have a second branch, which takes this information and then estimates the depth information for each one of the vertices. And finally, a third branch is the branch that we call it the shape branch, that enforces the 2D and 3D consistency between the 3D representation and the 2D projection of the joints. All right. So that's basically the idea, to try to introduce our knowledge on how this kind of problem works. We tried to introduce this knowledge in the network. So one problem, as Xavi mentioned, is the data. So here, this network requires training a lot of parameters, like 100 million parameters, something like that. And we didn't have enough data for doing this. And one typical approach that is done today is using synthetic data. You can create your synthetic data. In this case, we used Maya to create deformable objects with, we created like 120,000 images of deformable objects with different textures, replicating different types of clothes. And we changed also the deformation and the physical properties, right? And with this, we could train our network. And here I show you the results. So the results, we tried to evaluate this algorithm on different conditions. So first, on textures that were already seen on train, on textures that were not seen, in an important problem, which is non-texture. So that's very challenging, all right? When you don't have texture, most approaches in computer vision that doesn't work. So we also evaluated in this case. And then we also evaluated in cases of introducing synthetic occlusions. And here you can see the results. So for each one of the examples, I showed you this the estimated 3D shape from 2 viewpoints and the ground truth here, all right? And some numbers here. Basically, the idea is that we are slightly more accurate than non-deep learning approaches, but we have several advantages. First, we don't need to solve the 2D registration. 2D registration means to compute the 2D, the computation of the 2D mesh on the image plane is done by the network. In the case of the non-deep approaches, we need to provide this to the algorithms. And especially the most important advantage is that once the network has been trained, it is about 100 times faster than non-deep approaches. So another important thing I want to highlight from this table is that we also used ResNet. So instead of using this kind of modular structure of the network, we used a ResNet that, given the input image, tried to estimate directly the 3D vertices of the mesh. And this solution, this brute force solution, didn't work at all. So it worked well for textures that were already seen, but did not generalize to the novel conditions. All right. So that's another important message. Another example on real sequence. So here I show you the reconstructions we obtained with different non-deep learning approaches. And our approach, the color code, encodes the error. So basically, red means large error, blue a small error. So, and here again, we see that our approach is the one that provides the most accurate results. And again, the ResNet, so using the brute force solution, completely failed in this case. All right. Okay, so any questions for this section? No? Then how do you obtain the ground truth both in human pose and clothing shape? So in the case of the human pose, the ground truth came from mock-up systems. So there are large data sets. We didn't do this data set. So we used the data set that's called Human 3.6M, which has 3.6 million images of people walking around in laboratory in a laboratory. And there is a mock-up system that computes very well and very accurately the 3D joints. And in the case of the clothing, so that's what I showed here in this slide. So we used Maya. So we used Maya to synthetically render these clothes while they were moving, where they were being deformed, simulating the motion of the wind. So we hung it from 2 different points, and we applied a wind force, and we recorded this motion. And when you have these rendering tools, you have all the ground truth data. You have the position of all the vertices. You have everything. I hope this answers the question. All right, so let's move to the next work I want to talk is this paper on body and cloth shape estimation. All right, so here the motivation was on modeling 3D clothed humans. So modeling the geometry of clothed humans is an open problem. There are a bunch of papers today in the last EPR trying to solve this problem. So this was a paper from last year. So, and it was one of the first trying to tackle this problem. And another problem that we found is that there is no large and public data set of dressed humans, all right? So then the goals of our work were first to build the first large scale synthetic data set of dressed humans. And then we also proposed a representation for encoding the 3D shape that was very appropriate to train deep networks. And we finally designed a deep network to infer the 3D body and cloth shape. So what I want to also mention from this slide is that from these three parts, so when doing the paper, maybe we spent like 80% of the time building the data set and 10% building the representation and 10% building the deep network. So today, building the data set is very time costly, but then it helps a lot to progressing. So this is a data set that we created that is publicly available. All right, it's called the 3D people data set. It has about 2 million images of people doing different actions, 40 male and 40 female. So the images are recorded from different camera views, and we provide data with multiple cloth textures, the 3D model of the naked body, and also of the dressed of the geometry of the clothes. We also provide the skeleton, normals, depth, optical flow, etc. So this can be applied. This data set can be applied to a bunch of problems. So the most similar data set that existed is it was the Surreal, which was released 3 years ago, which has more images, but the main difference is that in this Surreal data set, they do not provide the clothes. So they only provide the model of a naked body. So, and you can see, I don't know if you can appreciate here, so this is a side-by-side comparison of the 3D people and Surreal. And on the Surreal, on the right, the clothes are just like body painted. So while in the left, on the 3D people, the clothes have their own geometry. All right. So, okay, once we have this data set, the first problem that we tried to tackle was the one of given an input image to, we wanted to estimate the 3D shape of the body and clothes. All right. And here we have the first problem. What is the best appropriate, the best representation to train a network to represent the shape? So do we have to use a parametric model, 3D point cloud, voxels, octrees, etc.? So there are many different representations that that can be used. So, but what is the best? So what we proposed in this paper was to use what is called the geometry image. So a geometry image is basically a representation that you take a 3D mesh, or in this case of a person, and you represent this mesh in a rectangular domain. For doing this this mapping, okay, we do in different steps. So in the first step, we project this 3D mesh on a sphere through an optimization process. Then we project this sphere on an octahedron, all right? Then we cut the octahedron and we unfold it to get this geometry image. And at the end, each one of the points here represents an X, Y, Z position of one point in the input mesh. So these two representations are equivalent. But training a network with these geometry images, it's much more convenient than using the 3D mesh. So then the problem that we have to solve is the following. Given input images, we need to train a network that learns these geometry images, which are equivalent to 3D meshes. Okay. Then this is the network that we created to solve this problem. The input was the image of the person, plus we also provided the 2D pose, and we created what is called a multi-scale regressor. That's a coarse-to-fine approximation of the output geometry image. And here, some of the results. I'll not go in detail with this, just to highlight this specific example where we have this woman dressed with the skirt. And of course, this is the SMPL, is the methods that use parametric models of the body shape that, of course, they couldn't solve this kind of problems. And for instance, in this case, they couldn't see that the one of the legs was raised. So, and this is the estimation that we obtained, right? So we kind of correctly estimated the pose of the person and the shape of the clothes. So more examples here on the top on synthetic data of our data set, and on the bottom on real images. You can see that our algorithm also worked for these crazy poses like this here, all right? And the results are quite consistent. Okay, so I want to move to the next, but before, I think also for the cloth example, the real thing is a t-shirt, and its ground truth shown is a plain cloth, which don't look, yes. So for the cloth example, we were assuming that we had rectangular topologies. So in the previous paper, not in this one, we were assuming that we knew the topology, and we just computed the deformation of the central rectangular part of the t-shirt. That's also an assumption that all the previous methods were doing. So it's hard, or still, I don't know, and I don't think there is a paper that can very well compute the 3D shape for topologically free shapes, right? Okay. And okay, let's move to the next part. But first, let me summarize what I showed so far. So I've explained it quite quickly, 3 different papers that solve regression models that basically estimate the geometry of the body and the cloth. And in these works, the training approach was fully supervised. So we, for all the training samples, we knew that this sample corresponds to this output. So what I'm going to explain now are 2 more papers, which are generative models that try to generate new images. In this case, we model the appearance of the body and the face expression. And another very important point and difference between with the previous ones is that those are weakly supervised. So we don't know the ground truth while training, okay? So that's very important. And that's one of the research lines that that is more important in deep learning. Xavi also mentioned this very, very quickly. So let's start with this person image synthesis work. So here, the problem is the following. The objective is the following. We have an input image and a desired new pose of that person, and we want to create a new image of how this person would be seen from this pose, all right? So this is a different pose, or from very different poses, all right? Even from the back. So all these poses are hallucinated, okay? And the main contribution is that, in contrast to the previous papers that solved this problem, we do not use full supervision. So our training set, so here is one training sample. So it has the input pose and the input image, but we do not use the output image, all right? So this makes the system also much harder to train, but also it doesn't require as much, it's easier to find a data set that, can be used for training. So how do we do this? So we built this network. At the first sight, if you are not familiar with deep learning, this may look a bit scary, but if we look at analyze it step per step, you will see that it makes a lot of sense. So first, we have this module here that we have the input image and the desired pose. And we have what is called a generator. The generator generates images. At the very beginning, the generator just renders pure noise, nothing. Okay. Then we add another module, which is called discriminator, to add photorealism, right? This is for maybe some of you know that this we use the same discriminator as PageGAN, which is another important paper. So when we add this photorealism discriminator, we force our generator to generate images, realistic images, but still they don't have the desired pose nor the identity of the input person. All right. To enforce this image here generated by the generator to have the correct pose, we add another module, which is a network that estimates the pose and enforces the constraint to have the same pose as the desired one. Now we have that our generator generates images, realistic images in the correct pose, but still this person is not the same as this one. And now that's a big problem because we don't have full supervision. So we cannot add a loss here saying, okay, we know that this person on this pose look like this and we can compute the loss. So what we do is what is called a cycle consistency. This means that we use the same generator to try to render back the input image, all right? So we render back the input image and then the loss is computed between this rendered back image and the input image, all right? And this part here on the right is the one that is in charge of computing the similarity between the rendered back and the input image. I hope this was clear. Some of the results that we obtained, the input image in the left column. In the second column is the 2D pose that we want to obtain, and this is our estimation. And here we compare with the ground truth. The ground truth, I want to mention that this ground truth is not used at all, so it's just as a reference, and you can see that there are cases where it's quite impressive what the network achieves, especially here when from just this input image of the woman seen from the side views, it can kind of hallucinate quite correctly how this person would be seen from the back. All right. But of course, since we are using so unconstrained data, we also have kind of funny or scary failure cases like you see here in the first example. So we could not banish part of the input phase from the generated image, or here the hand is taken as part of the pants, or here the pants are taken as interpreted by the network as boots. But anyway, we believe that pursuing this unsupervised kind of training is an important research that needs to be done. All right. Any questions on this section? Then let's move to the next paper here on phase animation. Here, the goal is the following. The objective of the work is building a system able to change the expression of a face from a single image. So we have this input image, all right? And we want to change the expression of this input image to all these different kinds of expressions. So changing one expression to a discrete set of expression was already solved back in 2018. But the main contribution of our work was that we could change this expression in a continuous manner. If you pay attention here to the videos, you will see that we smoothly changed from one expression to the other. And this is done using this single image as input. All right. So how do we achieve this? There are two main ingredients here. One, again, is the representation that we use. in this case, we use what is called the action units. Action units, basically what do they represent are different action units represent different motions of specific muscles in the face, all right? And then an expression can be represented as just a vector. That's a vector that represents the degree of activation of each one of the action units to convey the expression. For instance, here on the right, you see the action unit 45 represents the motion of the eyelid, or here the 25 represents the motion of the mouth. So an expression is just a linear combination of these action units, right? So that's the first main ingredient that we use. So the representation. A second ingredient that was very important also is the following, that we added what we call the self-learned face attention model. And the idea behind this self-learned attention model is the following. Let's say that we have this face, the input face, it's kind of neutral face, neutral expression, and we want to generate this smiley face. So if we want to generate this smiley face, observe that we don't need to, the network doesn't need to render again all the pixels of the image, all right? So the change of expression is just concentrated on a small regions of the face. For instance, this smiley face is concentrated here on the mouth, or also on the cheek. So the network just needs to re-estimate those pixels. And this layer here is like a delta on the RGB, so that this image, this output image of the smiley face is a linear combination of the input image with this mask and the delta of the RGB. So that's the expression of the linear combination that we use, all right? So with these two main ingredients, then this is how our network, GANimation we call it, is how GANimation looks at test. So we have an input image, and we also input the desired expression as a vector indicating the degree of activation of each one of the action units. And this is our generator, the generator of the mask, the delta of the RGB, and that's the output image that we obtain. So this is how GANimation looks at test. And at train looks, here I want to mention also that, again, like in the previous paper, we used, we trained this network in a weakly supervised manner. So we didn't have the full pairs of the same person under different expressions, right? So this is the GANimation at test, and this is how the model looks like a train. And if you kind of understood in the previous paper of generation of synthetic images, how it worked, so the procedure here is very similar. So here, basically our generator has two parts, two generators, one for the mask here, one for the mask and the other for the delta of the RGB. And again, at the beginning, we only have noise. We then force the generation of photorealistic images using a discriminator, all right? Then we force the network to generate the correct expression using a post constraint and the identity of the person with a cycle consistency again. So we try to recover back the original expression with the same generators. All right, and let me jump to the results here. So given an input image and the vector of decided expressions, these are the generated images. But if we can smoothly transition from the input image to the generated images by smoothly changing this vector here as a linear combination of the desired and the input expression. And that's what this expression here does. So if we smoothly change the condition, the desired expression from this input to the output, we can obtain a smooth change of expression that animates the face, all right? And here we just put all these image on a GIF, and you can see that very realistically the faces are, the expression of the faces are changed. And what was surprising also from this network is that it worked for non-anthropomorphic faces, like the one here on the right. So we at train, we didn't use any kind of non-anthropomorphic face, but it kind of also worked for these cases at test. So here another example of non-anthropomorphic faces, and here that's a cool example of what we could do with this animation. You can pay attention to each one of the characters and see how very realistically we can change the expression of each one of them. And here what was quite impressive was that we could smoothly blend the change of expression on top of the image. And this is thanks to this attention mask that smoothly transitions between the foreground and the background. Okay, this helped a lot. All right, so any questions for this part? If not, desired expression seems to be a vector. Yashguel asked, desired expression seems to be a vector. How is that vector decided if we want to generate? Oh, that's very good question. Yeah, nice. So we know that a smiley face, for instance, is a combination of a specific action unit. So there is a kind of table that tells you, okay, for a smiley face, you need to activate this action unit, this one with this level. So that we have to decide this beforehand. All right, good. Okay, so let's move to these two papers, the last two papers I want to talk about, in which we exploit the contextual information. The first one, we exploit the contextual information for motion prediction. Okay, so here the problem is that we want to solve is the following. We want to predict future human 3D poses from previous observations. All right, so we have a set of past human poses where the poses are represented by 3D skeletons, and what we want to do is to predict how these poses will be in the future, in the next T frames. Okay, so there are already some algorithms that solve this problem, but all the algorithms that solve this problem only pay attention to this kind of information, to the position of the skeletons. And what we thought in this paper, we said, okay, so the pose of a person can be very dependent on the context, on the layout of the scenario where the person is moving, etc. So that's what we proposed in this paper. In our approach, we wanted to exploit contextual information. So for instance, in this specific example, if we see these previous frames and we know that there is a table, probably we can infer that the person will walk around the table or will lean on top of the table. All right, so we want to use this kind of prior information. So how do we exploit the context of the scene? So we do it through two steps. In the first step, we learned the interactions between the objects. I will not go into detail, but here we use a kind of a specific type of networks that are called graph convolutional networks. So we train or we adapt the parameters of this network from the scene, from the poses of the past that we see. All right, so we assume that at T0 we have all the objects, and all the objects are representative of the scene, and all the objects are represented by a directional graph where all the edges are activated. And with the set of all past skeletons, we learn which are the important connections between the different objects. All right, and once we have learned this kind of graph, directional graph, we feed this to a network to do the prediction. Okay, here in this video, what you see is the kind of relations between objects that we learn, so the magnitude of the relation and also which are most important. So between the object and one of the humans, and between the humans and leather, etc. All right. So the first step is to learn these interactions, and the second step is fit these interactions to another type of network that is called a recurrent network. So here we have a recurrent network that does the prediction of the next skeleton pose based on the previous ones. But here we also use the information of these graph convolutional networks that encode the interactions between the objects. And I don't want to go into detail, but we have also another module that also does the prediction of how the position of the objects will change in the future. All right. Just let me show you some examples of what we obtain here. So here what you'll see are 2-3 examples where we compare the motion, the ground truth motion in blue with our context-aware model in red, and in green, another approach that didn't make use of the contextual information. And here on the bottom left in this graph, you basically see the error that usually typically is smaller in our case. So the red line is usually smaller than the green line, which does not use the contextual information. So in these next examples, you'll see that the non-contextual gets kind of stuck in doing the prediction, while our can more or less learn how the motion is performed. Right here, 2 people handling an object. Always the non-contextual one gets stuck. All right. So I'm going to move to the last of the papers. Is there any question here? No? All right. So the last work I want to talk about is this grasp affordance. So that's this was presented a couple of weeks ago at CBPR, and we kind of created a new problem for computer vision. So the problem probably it was already out there in robotics, but not in computer vision and human hands. So the problem was the following. Given an image of one or several objects, we wanted to predict how a human would grasp each one of these objects, all right? And the side effect of, or side result of this work was also that we estimated the 3D layout of the scene, okay? So why this can be useful? Direct applications that we can imagine is to teach a robot through imitation learning. So you can teach how an object needs to be grasped, and using imitation learning, the robot should be able to learn it. Also, we believe this kind of problem can be useful for virtual reality or augmented reality applications. All right, so since it was a new problem, there was no data set for that. So again, so what we had to do was to create a new data set, and that's the data set that we have created, the YCB-Object Affordance data set. Probably people from robotics know GraspIt, so we used this tool, GraspIt, to do this kind of annotations. We had 3D models of objects, and then with GraspIt, we just manually or semi-automatically, we put the hands to grasp each one of the objects. So we created this data set that at the end it has 130,000 K images. The number of objects is 21. The human grasp are split in a 33 taxonomy, so 33 different types of grasp. And at the end, we have about 28 million grasps. All right, with this large amount of graphs, we can definitely train a network. All right, and that's what I'll show you in the next slide. Here, that's the model that we use, the GanHand. So I'm explaining it slowly. So the first part of the network is a module that, given the input image, estimates the 3D layout of the scene. If the object is known, it just computes the pose of the object, like here. Or if the object is not known, it computes a point cloud, right? So these modules, we use one or the other, depending on if the object is known or not. Then, in the second part of the network, we have another branch that takes this input image and concatenates the mask of the layout and computes an image encoding. And this image encoding is then used to solve a classification task that, given this input image and the mask, it tells you which one of the, I told you that we used 33 different types of graphs. So it just solve one, it gives you an identifier of which of these 33 graphs is the best for this object. And this is used to compute a very coarse approximation of the hand. So with this branch here, we have a very coarse estimation of the graph. And then we have a final part where we use Mano. Mano is a parametric and differentiable model of the hand. So we have a hand that whose shape can be controlled by a number of parameters, like 50 or something like that. So we change these 50 parameters, and we can smoothly adapt the hand to grasp the object. So we had a coarse approximation here, and with the Mano model and some losses that try to prevent interpretation, we get this good grasp. So let me show you some examples. That's the initial estimate. So the initial estimate means the estimate that we have here, the coarse hand estimation, all right? And then you'll see how with the second part, with this part here, we do the optimization. You see here, so the optimization adjusts the position of the hand on the surface of the object. And so here, that's, oops, sorry. Let me play it again. What I wanted to show is that here, in this specific example, the coarse estimation, you see that there is even interpretation of the hand and the 3D model. But then when we apply the optimization, this is solved. So in this case, I'm showing results on synthetic data, but we also applied this to real data. That's what we show in this video here. So we have multiple objects, and we show how we can grasp each one of the objects. All right. And with this, I would say I finish my presentation. All right, are there any questions here? Otherwise, I'll do a very quick conclusions. So just very quick conclusions. So what we have presented are different strategies for improving the performance of deep networks to model humans. One of these strategies, unfortunately, it's not very pleasant, is the construction of the data sets. But we need to suffer on that, and we need to do it. And we have presented two data sets, the 3D people data set, the YCB-Affordance data set that we made publicly available. Then what is more important, and you need to think more about that, is what kind of representation do you want to use to represent to train your data. So, and I showed you some examples that just using Euclidean distance matrices can be very convenient. Instead of using 3D meshes, you can use the geometry images, so the action units, or how we can use a graph to embed the contextual relations. And I've presented different networks with different properties. Some of them can be trained in a supervised manner, others in a weakly supervised manner, others allow you to reason about the context. And I finish here, but before finishing, I need to give a big thanks to my collaborators, and especially here, Albert Pumarola and Enrique Corona, who are the first authors and the main responsibles of all the papers I've explained today. Albert will later on explain, we'll do a workshop, and I think in the next session, explain some details on generative models that he has been used in this paper. So with this, I finish, and if you want to ask anything.
Yes, you have a question, Francesc?
Yash Goel asks, the desired expression seems to be a vector. How? No, is the same. No, I already responded to that question. Yeah.
Yes, in the last one, human motion.
In human motion prediction, how is the environment table star modeled for the network, as they have different shapes? Also, how is selected which is the object area of interest of the context? So in the case of the representation of the objects, what we assume that we have a bounding box, a 3D bounding box of each one of the objects. And the representation of the objects is at the end just the bounding boxes. If we could have any other kind of representation, but in that case, we only used the 3D bounding boxes plus, I think, an ID of the type of object. So at the end is a vector encoding this kind of information. And also, how is it selected which is the object area of interest for context aware? All the objects are initially considered. So here, at the very beginning, all the objects are considered. All the objects of the scene are considered. So the nodes of this graph are a state vector that represents the object. As I said, here is the bounding boxes plus the identity of the object. And initially, we have all the possible connections between all the objects, even the object by itself. And the network iterates, and the graph convolutional learns which are the best connections. So this is done with this graph convolutional network. So at the end, it decides the network itself using this training data. It learns which are the best connections, right? I don't know if this answered. And then I have another question here. Are there any assumptions on the person's height for 3D body pose estimation? Another very good questions. Yeah, that's an open problem. And the problem is that the height of the person will depend on the height of the persons that you have used for training. So in our case, we trained the data with the H3.6M dataset, which has adult people, so grown people, which is people that is between 1.60 m and 1.70 m. If we used the same algorithm to estimate the shape of a kid of less than a meter, yeah, the network would estimate that, would infer that its height is like the height of an adult. So everything depends on the data that you have. So that's that's still an open problem that we are trying to address, but we don't have the solution yet. Good question. All right.
All right. Thank you very much, Francesc.
Thank you.
So I think we have a last question. Can you read the chat?
Can the same network be used for pose estimation for animals? Definitely. But here the problem is the data set. If you provide us with a data set of animals and skeletons of animals, we can train the network, exactly the same network. We just need to change Probably if you have a different number of joins, we need to change do very small tweaks and changes. But the main problem here is the data set.
Okay.
All right.
Thank you, Francesc.